Hi, I'm Greg. I work in risk management at RBC.
Hi. Okay, go ahead.
Oh, I'm Lucy. I'm in the data science team.
And I'm Layli, and I'm also in the data science team at RBC.
Okay. So in risk management, my job is to think about what do we need to do to be able to trust the models that we have in the bank. And something we've been thinking about now is how do we trust our machine learning models? So model validation in banks has been something that we've been doing for decades, but now we're starting to think, well, what is different about machine learning, and what do we need to do differently to be able to trust the models that are being developed these days? So the basic idea is that with traditional models, the modeler imposes assumptions, and the validator can inspect those assumptions and determine if those assumptions work well for the use of the model. With machine learning models, it's a little bit more difficult, where we now have the model learning its own assumptions from the data in some sense. So with a traditional model, you might think that, for example, the developer needs to impose a functional form, but for a machine learning model, the algorithm finds the functional form based on the data it's given. So that presents a challenge for the validator. You can think of it as the validator needs to find a way to discover what the model has learned in order to test it. So something I hear fairly often is, well, Greg, the machine learning models are actually quite old. They've been around for a long time. A regression model is a machine learning model. That's been around for a long time, and we know how to test those. So what's different about machine learning? And the answer that I have to that is yes, those types of models have been around for a long time, but the models that we're starting to use now in the bank are different in the sense that they don't have the same level of transparency as traditional models. So there's a couple of ways you can think about transparency. Broadly speaking, you can think about transparency in being you understand how the model works. But more specifically, you might think, okay, if I can inspect the entire model at a glance, I can see, the functional form, I can see the parameters, I can understand how it works, then the model is transparent. Another way you might think is that if you can look at each parameter in the model and associate an intuitive explanation with that parameter, then the model is transparent. Or you might think that if you can understand how the algorithm itself works, the model is transparent. So an example of that, if you've ever taken a statistics course, is that the linear regression is the best linear unbiased estimator. So you have some idea of a guarantee based on what you know about the algorithm itself. But for non-transparent models, it's difficult to know what the algorithms are learning, largely because they have a lot of parameters. So you might be dealing with a model with thousands or millions of parameters, so it's not a transparent model in that case, and you need to do something different. So to give you some intuition about the challenges that this presents for the model validator, I have two examples. One is from the text domain, and one is from the image domain. So on the left, I have an example. Both examples are from the academic literature, but on the left, I have an example which is a sentiment classifier for movie reviews. And basically, what this model does is say whether a movie review is positive or negative. So you might think, if I've trained my model on a data set that has an example where the movie review says this is a great movie, and we've told the algorithm, well, a great movie, that's positive. You might hope that if you give it a review that says the movie is good, it'll know that that's positive. But what these researchers showed is that's not always the case. So they came up with a very clever way of splitting the test set so that you don't see the same words in train as you do in test. And what they found is that, lo and behold, the movie is good. The algorithm didn't know that was positive, and they attributed that to the fact that the algorithm seemed to memorize specific words rather than understanding something more fundamental. So that's actually quite surprising from a validation perspective, and the point here is that you need to come up with a clever test to be able to identify that the model is going to fail in that way. On the right side, there's a picture of a cat. So this is an image classifier which correctly guesses that this is a cat. And what these researchers did was create the image on the right, which is the same photograph, but it has elephant texture on it. It's elephant skin. And here the algorithm says with some degree of confidence that this is now an elephant. And again, that's surprising to a human because most humans would look at that and think that's a cat. And what the researchers concluded is that the algorithm has learned to recognize images based on their texture, whereas humans tend to recognize images based on their shape. So what they did is they generated the images at the bottom. You can see that it's the same image of the same animal each time, but it's shown in a different style. And they gave those to the algorithm. And after training it on those, they found that they were able to teach the algorithm to recognize by shape rather than by texture. So again, that's a very clever way to test a model and find that it's learned something surprising, and that you can see that it might fail in a surprising way if you don't have these tests. So with that, I'll turn it over to Lucy to explain how we're going about testing our models at RBC.
Okay, thanks, Greg. As Greg mentioned, AI models become more and more complicated black box solutions. And also, AI model cannot be blindly trusted. How can we make it more trustable? It's really hard topic now. We already saw a lot of talks during this conference. Actually, go back to RBC. We started this work back to 2 years ago. We built RBC internal model validation tools to increase the model trust, at the same time reduce risk, and also reduce model validation time. When we design and develop these tools, we think about two areas. One is from user perspective, another from governance perspective. From user perspective, no matter how complicated the algorithm is, easy always is the key. So we offer easy access by web service and also GitHub. So different users may choose different access. For example, technical people may like GitHub more. We also offer the visualization to help users to understand our solution and also explain to non-technical people. Everything we build on the internal cloud environment that's easy to scale. From users' perspective, that means they are able to quickly to get their solution. From governance perspective, we build standard tests on standard Python packages. We always choose the most reliable and trustable package to build our blocks. We are not only make the developer model transparent, you will see in our later talk, and also make model validation transparent. We build everything on the open source environment. Also, our code completely open inside RBC. Everyone able to download, use it, and also make contribution on top of it. We offer multiple choice for user to choose. Different scenario, different use case may choose different tests. We assume the model is completely black box solution. We only have input, output, middle black box, and not as a traditional model, it's white box. How we evaluate this black box model? First, performance. We look at model performance from like accuracy and also stability side to make sure our model have high quality. Because it's black box model, it's really hard, for business to understand it, to trust it, and also implement into their business case. So we build global and individual interpretability to open the box, as Greg mentioned. That's very important to increase the trust. We also integrate our another self-service tool, actually my team built on, it's AutoML2, to challenge developer model. We compare the developer model, people model versus the auto model, and see what's the difference. The last one is fairness. We want to make sure our RBC model completely fair to everyone. We don't have any discrimination problem. Next, I will pass to Lily to look at details.
Okay, my job here is to provide you with an overall insight of our Trustworthy AI package. I'm not going into much technical details because we found it out of the scope of this business section. So first of all, I'm going to start with explaining a use case. It's actually the German credit data set. It includes the information, or as we can say, features or attributes for different loan applicants, features like credit story, credit amount, duration, etc. Suppose we want to build a model to predict the credit score for different loan applicants, and based on the credit score, decide whether to accept the loan or reject the loan. If we choose to use a simple model like logistic regression or decision tree, we would be happy because these kind of models are sort of interpretable. For example, you can look at the whole structure of the decision tree and see how it goes down from the top node to the down level nodes. Yeah, but the thing is that there is a tendency everywhere in every industry, and banking is not an exception, to use more complicated machine learning models to get better performance. And the problem is that more complicated machine learning models are less interpretable. So what we do, after a model has been developed, we pass it to our Trustworthy AI package to get some knowledge and insight of the model so we can trust the model more. First of all, I'm going to start with our interpretability sub-package, which is included in our Trustworthy AI package. We have some methods for global interpretability, like what are the general rules approximately behind the model? What are the most important features to the model? Or how each feature impacts the model output? This kind of interpretability methods are mostly used by the model developer or model owner or the model validator or the person who is using the model for a specific application. Besides global interpretability methods, we have some individual interpretability methods, which we use to explain the model prediction for a specific individual. Look at that little guy on the top right hand. His name is Sam. Sam is sad and also confused, but why? Because his application for loan has been rejected. So one of the intention of individual interpretability methods is to explain to Sam why he has been rejected. One of the basic functions or methods that we have for global interpretability is feature importance, which is based on random permutation. What it does is quite easy. For example, if for a specific feature, it shuffles the values of the feature over the whole data set and check how much is provided model performance metric, for example, accuracy changes by shuffling the values of that feature. More change in the performance metric shows that that feature is more important to our model. For example, for the given use case, we see that status of checking account, duration, and credit amount are the top 3 most important features to our model. Another basic function that we have for global interpretability is partial dependence plot, or PDP. It shows the relationship between the model output and a specific feature or pair of features. For example, in the previous slide, we saw that duration was one of the most important features to our model. So we may want to check how is the relationship between our model output, which is the credit score, and duration. As we see in this PDP plot, the credit score increases kind of monotonically by increasing duration and becomes flat at a certain point around 30. Well, by giving these 2 basic examples of global interpretability, I think now you have a good sense what we mean by global interpretability. Now I'm going to explain a little bit about individual interpretability. One of the functions or methods for individual interpretability is local interpretable model agnostic explanation, or LIME. We have actually leveraged the open source package of LIME in Python and integrated it in our Trustworthy AI package. We use LIME to explain the model prediction for a specific individual. If I want to explain how LIME works in a simple way, it's actually very simple. For example, you have a complicated and nonlinear model. You approximate the model behavior around a specific individual feature values using a more interpretable and simple model, for example, a linear model, and use that interpretable model to explain the model output and model prediction for that specific individual. For example, if it's a linear model, what is a linear model? It's the weighted sum of the feature. So what is the contribution of the specific feature? It's feature value times the weight of that feature. So as you can see, for example, here for a specific individual, status of checking account duration impacts the model output in a positive way, installment plan in a negative way, and so on. You remember Sam? He was confused and also sad. He may be still sad, but not confused anymore, because at least he knows why he has been rejected. Another method that we have for individual interpretability is counterfactual explanation. It mostly can be used by the end user. For example, we have productionized a model, and it's been used in the bank for making decision to accept the loan or reject the loan. We see that for a specific individual, the model decision is rejection. We want to know how we can change some features so we can reverse the model prediction to acceptance, or model decision to acceptance. The thing is that we want to change as little as possible, and we want to change as few features as possible, and we want the change in the features to be kind of likely and feasible. In our counterfactual explanation function, an optimization problem is solved behind the scene, taking account all these considerations, and then after that it gives us out the counterfactual explanation for a specific individual. Here is Sam again. Sam, he seems to be happy now, because at least he knows what to do so that he can get approved for the loan. We have a couple of more interesting and advanced methods for global and individual interpretability, but because of the time limit, I won't explain them. If you are interested, please reach out offline. We have also fairness package in our Trustworthy AI package. We have some methods for group fairness. What do we mean by group fairness? For group fairness, we generally have a sensitive attribute. For example, gender, race, maybe age. And then divide the whole population to different groups based on that sensitive attribute. For example, for gender would be female and male group. And female group is usually considered as a disadvantaged group. And we check if our model treats these different groups equally. We have also some methods for individual fairness to check if our model is fair to a specific individual. For these methods, we look at a specific individual and look at also its neighboring individual. And by neighboring individual, we mean the individuals who are similar to our specific individual based on the feature values that they have. So we check if our model treats our specific individual the same as its neighboring individual. For group fairness, we have included different criteria, or as we can say, definitions for fairness, independency, separation, sufficiency. and have different metrics to check if our model violates any of these criteria. For independency, for example, we check if our model score distribution is the same for the different groups, for example, male and female. For separation, for example, we look at the ROC curve for different groups or the false negative rate for different groups and want them to be almost equal in different groups. For sufficiency, for example, we generally look at the calibration plot for different groups and want them not to be significantly different from each other. As I mentioned, we have also some methods for individual fairness. For individual fairness, we look at a specific individual and then find its neighboring individual, for example, by k-nearest neighbors. And then check if our model output for our individual is the same as its neighboring individual. And if it's not the case, we may conclude that our model is not fair enough to our specific individual. We have two methods, consistency and situation testing, for individual fairness. As Lucy mentioned, we also have a sub-package for AutoML, and one of the main goals of having such a sub-package is for benchmark modeling. For example, we have developed a model, and before productionizing that model, we pass the model and also the data to our AutoML package. What it does, it first just does some data profiling and data preprocessing, like outlier detection and removal, missing value handling, feature engineering, etc. And then find the benchmark models by tuning the hyperparameters, and ultimately selects the best model based on the given performance metric. After that, we look at the different performance metrics for our benchmark model, and if our benchmark model outperforms the developed model, we may reject the developed model. I hope I was able to give you an overall insight of our Trustworthy AI package. Now I'm going to pass to Lucy for the final remarks.
Okay, let me quick summary what we have. We introduced RBC internal model validation tool, Trustworthy AI, to increase model trust and also reduce model risk. Inside, we have 4 key packages: interpretability, performance, fairness, and AutoML. We look at the model from full angle to make sure model have high quality and also trustable. Next step, we will continue work on the existing package, make it more powerful, and also at the same time, we will build some new package based on Greg team's requirements. We also like to build RBC AI community to leverage our high technical infrastructure, rich database, connect with business, data scientists, data governance, and risk management to make RBC to be an AI-driven bank in the future. Okay, thanks for your listening. Any questions?
So for your, the machine learning model, generally compared with the, the regression model, so how much is the lift, the improvement?
That's completely based on the data itself, right? Some data are, for example, small data cannot be lifted too much. But if the data is huge, that definitely lifts a lot.
So what's the maximum lift you achieved?
So based on our limited test, maybe 10 to 20%.
That's for AUC or KS?
I will say more like I think that's the KS. Yeah, I think that's the KS.
Okay, thank you.